Here we go. All right, so today we have the pleasure of having Dr. Mohammed Osman, who's going to talk about quantum computing. So Dr. Osman, I hope I'm pronouncing this right,
yeah,
Osman?
right.
Yeah. So he's a senior lecturer at the School of Computing and Information Systems and the School of the Melbourne School of Engineering. He's leading a quantum computing research and education program. And after his PhD in 2010 from Purdue University in America, he held positions at the Center for Quantum Computation and Communication Technology and the School of Physics at the University of Melbourne. He has worked for many years on spin qubits in silicon, quantum gates, and quantum computer architecture designs for scalable, fault-tolerant quantum computing. He holds several patents for surface code architecture design and machine learning-based autonomous qubit characterization. In recent years, he has focused on the design of quantum simulations and algorithms for noisy intermediate-scale quantum devices. Dr. Osman is a recipient of many awards and fellowships, including the Dean's Award for Research Excellence and fellowships from DAAD, and the prestigious Fulbright Fellowship. So without further ado, let me pass on to Dr. Osman. So the stage is yours, Dr. Osman.
Yeah, thank you very much, Kevin. And thank you to IEEE University of Melbourne branch for giving me this opportunity to talk about quantum computing. It's really a pleasure. So I'm going to talk about quantum computing fundamentals and applications. So this talk is basically not like a research seminar or advanced talk, rather it's a very fundamental talk, and the target audience are undergraduate and MSc students who are probably interested in learning about quantum computing or who are looking to do research in the area of quantum computing. And also this talk is for everyone else who is just fascinated by the potential of quantum computing to solve real world problems. So what I'm going to cover is, I'm going to first talk about evolution of nanoelectronic devices in the last few decades and how we reached quantum computers. Then I'm going to talk about bits versus qubits, because we all know bits are in your normal computers and quantum computers will be made from qubits. So I'm going to make a distinction between those two. I'm also going to talk about digital circuits versus quantum circuits. How can you build quantum computers? And then I'm going to a little bit talk about classical computing versus quantum computing. And finally, some topics of recent quantum computing research. So if you're new in quantum computing area, or if this is your first talk on quantum computing, then I hope there'll be a lot of fundamental materials to learn about it. But if you're already an expert in quantum computing, then there'll be more interesting stuff towards the end of the talk. So initially, it will be a little bit of basic and boring stuff, and at the end, you'll find some exciting stuff. Okay, so before we go to quantum computing, let's first talk about the evolution of nanoelectronic devices in the last few decades. And if you look at the progress, there are three major driving factors: size, cost, and capacity. So in the last few decades, all the progress in nanoelectronics has been around these three factors. So we want to make devices small, so size matters. We are trying to make devices smaller and smaller. We want to have cheaper devices, we want to reduce the cost, and we want to increase the capacity. So we want to pack more capacity into the same device. For example, memories. If you look at the memories back in 1950s and 60s, memories were very large, they were very heavy, but their capacity was very small. So you can see that on the left side, it's a very large size memory, but 62 kilobytes, very small capacity. And it was pretty expensive too. But nowadays, you can go to any shop, for example, Officeworks, you can buy a 256 gigabytes of memory, which is very, very small. You can literally put it on your finger, and it's very cheap too. So that's the progress that has happened during the last decades. And even in the future, we are expecting that memories will be stored in single atoms. They are even becoming smaller and smaller. You will have single atom where you will store your information. So you can see that the evolution has been driven by size, cost, and capacity. Another example is imaging. For example, if you're familiar with MRI, the machine which is shown in the left bottom corner, they are very big and they're very bulky, and because they require large magnetic fields. But there's already research happening where you can use single atom spins to sense these magnetic fields. So in the future, there is a hope that you will have single atom magnetic probes, which you can insert on your biological system, and you can basically image the biological systems at atomic level. So again, you can see that the size is becoming very, very small. The efficiency or the capacity is increasing, and hopefully the cost will be very small too, because they will be made up of single atoms, very small sizes. Of course, computing has seen the most dramatic and amazing progress in the last few decades. If you look at the early computers, for example, in 1940s, they were really, really large. Like, in order to put a computer, you need a very big hall, and their efficiency was very low as well. But nowadays, you have laptop computers, you have mobile phones, and you can do pretty much anything on these devices. So their size is very small, they are very cost effective, and their capacity is enormous. So the question is that how did this happen? So mainly this power in computing is driven by the scaling of the transistor. So Moore's law, which is very famous and which was presented in 1965 by Gordon Moore at Intel, and he predicted that when the technology progress, you can basically reduce the size of the transistor to half every 18 to 24 months. And that way you can have the same area of the processor, and you can pack double the amount of transistors. And you can see that from this curve that I'm showing on the left side, the transistors has been constantly reducing to the half every 1.5 years. And that has been increasing the capacity of the microprocessors. Right now, we are at the level of around 10 to 15 nanometer node. And in parallel, Richard Feynman, who is a visionary scientist, he predicted that we can even go beyond that scaling, and we can actually use single atoms to do this computing. We can have single atom memories, we can have single atom as a basic building block of your computing machines. And that will be enormously powerful because, first of all, you don't have to do any scaling. Like, atoms are literally the fundamental unit of any material. So if you can use atoms, you are already at the fundamental level. So you can pack huge amount of memory, you can pack huge amount of computational power in those devices. But at the same time, for example, if you are simulating nature, which is fundamentally quantum mechanical, then having a quantum machine will be very useful to simulate those nature's phenomena. So that was the basic motivation behind quantum computers. Although this has been around for many years, but initially the progress was very slow because the technology wasn't there to manipulate and process single atoms. During the last couple of days, now the technology has progressed to a level where we can actually look at individual atoms, we can manipulate individual atoms, and therefore quantum computing is becoming closer to reality. So I just want to highlight this Feynman's dream in 1960s, 70s, which he envisioned that you can have a single atom transistor. And that was done actually in 2012 in this Nature Nanotechnology paper demonstrated by Australian researchers at UNSW, where they were actually able to make transistor by a single atom. So this is kind of like ultimate scaling of your transistor. So right now we have billions of transistors packed in microprocessor chips, and we are kind of reaching the end of Moore's law. We cannot make transistors further small. We cannot pack more transistors into the same chip because so many billions of transistors packed into such a small area, and they're turning on and off, so generating so much heat that you cannot keep the microprocessor chip cool. So we have to look at other ways to enhance computational power. And there are already, people are looking at different ways of doing that. For example, carbon nanotube-based transistors. There are other spin-based technologies where you can extend the computational power of the current microprocessors. But in parallel, a radically different approach is emerging and progressing, and that is called quantum computers. Quantum computers are totally different from your normal microprocessors, and they are expected to offer enormous computational power. And that's what I'm going to show you in the rest of my talk, how quantum computers are different from your classical computers, and how can you achieve enormous computational power from these magical machines. So let's talk about quantum now. As we all know that from our high school physics, that everything that we see or observe in our world around us, that is classical mechanics. That's basically followed by Newton's law. People running, aeroplanes flying, apples falling from the tree, everything is following nicely Newton's laws. And that is called classical mechanics. However, in early 20th century, scientists, when they started to look at atoms and inside atoms, they started to realize that the physics at that small level is very different. It's not obeyed by classical mechanics. You need a different laws to understand that physics. And then the quantum mechanics was born. And so at the very small level or scale where you are looking at electrons and properties of electrons in orbitals, you probably will remember the famous Bohr's atomic model from your high school physics, which basically says that electrons can only be in discrete energy levels. And in order to go from one energy level to the another energy level, you need a certain amount of energy. So that's cannot be explained by classical mechanics. That's all quantum mechanics. Photoelectric effect, for example. If you shine light, you can change the energy of an electron. That's also quantum mechanical property, which is not explainable by classical mechanics. So when you go to very small scale, things behave which are not explainable by classical mechanics. You need quantum mechanics, which is a totally different theory to explain your observations. But one interesting aspect is that even the nanoscale devices, not the quantum, I'm not yet talking about quantum computer, just the nanoscale devices like your ordinary microprocessors or your light sensors or light emitters, they all follow quantum mechanical principles because they behave because the fundamental units that, or the fundamental thing that is governing their operation is electrons, right? So for example, in light emission, you shine a light and you change the energy level of electron, or when electron changes energy level, you get light photon out of it. So this is all quantum mechanics. So why quantum computers are then different? Because in quantum computer, we are going even further at fundamental, ultra small scale, even more fundamental than your nanoscale devices. Here we are talking about individual electronic spins. We are not talking about electron changing an energy level and giving you light, or electron flow in the transistor, making it on and off. We are actually talking about single electron and their spins, or we are talking about single photons and their polarizations. And at that level, even more magical things are happening. Even the things are more different. For example, you observe entanglement, tunneling, superposition, which I will explain in the next few slides. And even those things are different from what you see in your normal nanoscale devices. And that is what gives quantum computers all the power, as you will see in the next few slides. So let's look at the bits versus qubits. So in normal computers, we have bits. By bits, I mean your fundamental unit of information is either 0 or 1. But in quantum computers, we have qubits, which are different than bits. And how are they different? So as I said, bit can only be 1 or 0 at a time, only 2 possible values. But for example, if you are doing a coin toss, you can have either head or tail. However, in qubits, you can have 0, 1, or any superposition of them. So by superposition, I mean you can generate a state which is alpha times 0 plus beta times 1. And now you can select values of alpha and beta. For example, you can have a situation where you have 90% of 0, 10% of 1. This is not available in your classical computer because remember, only it can be 100% 0 or 100% 1. So that is different in quantum computers. Qubits can be in superposition. They can be in any sort of combinations of 0 and 1s. And in other words, we can say that you basically toss a coin, and you can have the outcome of the coin toss would be 90% head, 10% tail. It's very different thing. So that's why when we represent qubit state, we use this sphere, which is called block sphere. So this block sphere says that this vertical axis is 0 state going upward, down is 1, for example. But then you can basically rotate it, right? So this alpha 0 plus beta 1 is the rotation of those vectors. So you can basically rotate the qubit on any point on the surface of the block sphere, and that will be a valid qubit state. And you can already see that alpha and beta are continuous numbers. They are continuous complex numbers. So you can have only one qubit which can go to many different states, infinite possible different states on the surface of the block sphere, and that gives the qubit amazing powers. However, we need to make sure that the state is always normalized. So that's the condition. For example, always alpha square plus beta square should add to 1. So the state is always normalized, just a technical detail. So now let's look at like how would you get the enormous power out of these qubits? So what sort of computational space is available if we have 3 bits versus 3 qubits? So we know that 3 bits will give you a state like 0, 1, 0, right? This is one possible configuration. You can have 1, 0, 0, you can have 1, 1, 0, whatever, right? I mean, the 3 bit at any particular instance of time, the 3 bits will have a 3-bit information, which is a single number. On the other hand, 3 qubits will have a state which will be a combination of all the possible 8 combinations of the bits, right? So it will have A times 0, 0, 0, B times 0, 0, 1, C times 0, 1, 0, and so on. So you can already see that a 3-bit number is just a 1 number. A 3 qubits can have combination of all the possible 3-bit configurations, and that means you will have now an access to a 2 power 3 dimensional Hilbert space. So you can prepare a state which can cover any point inside that 3-dimensional 2 power 3 dimensional Hilbert space. Now, what if we have 300 bits versus 300 qubits? Well, 300 bits will give you this very large number. It is very large, but it's just to one number. But what if we have 300 qubits? That is basically equivalent to a Hilbert space of 2 power 300 or 10 power 90 dimensional space. So you can basically represent 10 power 90 different possible things by just 300 qubits. And just to remind you the large size of this space, total number of atoms in the universe are about 10 power 78. So if you have a 300 qubit state, you can basically easily represent all the possible atoms in the universe. You can encode them in that state. So that's the enormous power of quantum computers, that if you have qubits, you have access to very large computational space. Then another magical property of quantum bits is entanglement, which is not present in your classical computers. So it's a special property. And what do I mean by entanglement is that, now suppose you have 2 coins and both coins are independent and you just do a coin toss independently on both. Since they are independent, there's equally likely chance that you will get either head-head, tail-tail, head-tail, or tail-head, right? So you will have equal chance, 25% chance of getting any of these 4 combinations. But in quantum computing world, you can actually make those 2 coins coupled such that when you toss them, you will get head-head with 50%, tail-tail with 50%, and you will never get head-tail or tail-head combination. That is not possible classically, but in quantum mechanics, you can prepare a state where you can basically couple the states in such a way that some outcomes are much higher, have much higher probability than the other outcomes. And that is called entanglement, a magical connection between the outcomes. And this was really hard to understand. I mean, still very hard to understand. Even after 100 years of research, this is really hard to understand. How is this happening? This is just a property of quantum mechanical systems. Even Einstein had a hard time understanding it, and he called it a spooky action at a distance. However, by doing entanglement in experiments, you can do teleportation. You can transfer information from one place to the other place without physically moving the information. Remember that magical thing in Star Wars movies where you can basically have person standing on one place and then all of a sudden disappearing and appearing on a second place, right? So that's teleportation. So you could do by entanglement. You can move things from one place to the other. Dense coding, you can have two classical bits of information stored in one qubit. So you can basically encode much more information in much less amount of memory space. Well, all is not good. There is a weakness of these qubits, which is called decoherence. What I mean by decoherence is that since the qubits are formed by spins of electrons or polarizations of photons, they are very delicate. So you can basically consider a qubit as a bubble, a quantum state as a bubble. And as you already know that if you touch a bubble, or if bubble touch anything in the environment, it pops. It doesn't stay as a bubble. It doesn't stay into a coherent state, right? So that is same with qubits. So you have to protect qubits. If qubits come in close contact with any environmental thing, like for example, noise or any circuit noise or anything that's happening close to qubits, that would decohere the state. That will basically make loss of information. For example, if you have a prepared state, which is a combination of head and tail, the decoherence would mean you will go back to your classical state, like you will either have only head or tail. So you won't have a combination of both together. So that's the biggest weakness of qubits, and that's a big area of research. How can we extend the lifetimes of the qubits? How can we protect them from the environment so that they don't decohere? Because if they decohere, you lose all the magical properties of qubits that I've been talking about. So you want to basically really keep the qubits away from the environment where they can stay in the superposition or entangled state and process the information that you want to process. Another thing is about measurement. So you can't even measure the qubits, right? So in a digital circuit, at any point during the circuit, you can look at the state of the circuit, right? You normally, this is how you do the debugging, right? So you have gates, you don't get the right output. Okay, I go back and I see my circuit at different points and I can find out where the error is happening. That is not possible in quantum computers. In quantum computers, you have prepared your input, and then at the end, you can measure the output. You cannot look at the states in between, because measurement is also a decoherence. As soon as you will measure the state, it will again decohere it, and you will lose all the properties of your quantum system. So that's really the challenges which we have to overcome as scientists or researchers to really make an efficient quantum computer. Okay, so let's suppose we have qubits and we have protected qubits. How can we make circuits out of them? How can we do computations? So I'll just give you some ideas on like gates, on bits versus operations on qubits. So we all know that in classical circuits, you have gates, for example, AND, OR, exclusive OR, and all different kind of gates which acts on bits. And then there are Boolean tables, well-defined, and then you get the outputs, right? But the key thing here is that since your inputs to these gates are finite bits, like one deterministic values, either 0 or 1s, and then your output of the gates is also deterministic. It will be either well-defined 0 output or well-defined 1. However, in quantum computing, as you know that, as I've showed you previous slide, that the qubits are in superposition state. They are not always 0 or 1. They could be combinations of 0s or 1s. So quantum gates are basically operations on those quantum states. So they basically take a quantum state, which can be combinations of 0 and 1, and then they can basically change those weights. For example, if a state is passed, like alpha 0 plus beta 1 state is passed to a quantum gate, it could generate a new state with slightly different alpha and beta. So it can change the states. So there are lots of gates in quantum to make quantum circuits. For example, quantum NOT gate, Z gate, C NOT gate. I'm not going to go into detail. I'm just trying to give you ideas of how quantum computers operate. But just keep in mind that quantum gates are different from your classical gates, because qubits are very different by nature from your classical bits. And quantum computers can change not only the amplitude, but also the phase, because as I said, these alpha and beta could be complex numbers. So they have a magnitude and a phase. So a quantum gate can act on a qubit, and it can either change the amplitude or it can change the phase of it. So we have to keep track of the amplitudes and phase when we process a quantum circuit. So that's how you make a classical circuit. You connect a bunch of gates, and you basically you have inputs here. Those pass through a bunch of gates, and then finally you get the output F. Very similarly, we have input qubits here. Typically, they all initialize to 0. That's how we start quantum circuits. We initialize to all the qubits to zeros. Then we have different gates like Hadamard gates, 2-qubit CNOT gates, different gates. And at the end, we do the measurement. Because at the end, not like a classical circuit that at the end, you will always get a bit value. Here you have a state, some combination of zeros and ones, right? So you want to measure what is actual output of the circuit. So you have to have a measurement device. So the things that you need to know about quantum circuits versus classical circuits is that quantum circuits process complex numbers rather than just the zeros and ones. There could be superpositions in entanglement, and then there are probabilistic amplitudes. And at the end, you have to do measurements and all that. I think in the next slide, I'll give you a more idea of how a quantum circuit works when I'll show you the working of a quantum circuit. So let's first very quickly look at the implementations. How can we make a large scale quantum computer? Because we can't make a quantum computer out of few bits or few gates, right? So you have to have large number of qubits, large number of gates connected in a way that you can have a whole computer, which can then solve the real world problem. So let's look at the implementation. Quantum computers can be made by different kind of qubits, like different kind of materials that can be used to make qubits. For example, superconducting, trapped ions, photonic, silicon-based topological, different kind of materials that you can use. Each material has its own properties, like how many qubits you have already made, what is the qubit lifetime, like lifetime means how long qubit can stay in its state before decohering. So that's called a lifetime. Fidelity is like how much is the accuracy. So all these different properties. So different materials offer you different properties. My research is mainly based on silicon. Silicon is very popular material, like all of your current microelectronics is based on silicon. So we are trying to use silicon to make quantum computer as well. And as you can see that it's a really nice material. It gives you very long coherence time. Like your qubits can stay in their state for seconds. Or even sometimes minutes, and that is enough time to perform quantum computations on those qubits. Also scalability. Silicon qubits are very good in terms of scalability. You can make very large systems out of it. So that's the motivation behind making a silicon quantum computer. So these are some examples of different quantum computers that exist at the moment. For example, IBM, the most popular company developing quantum computers. So they have currently 20 qubit, 16 qubit machines. I think the largest machine they have is 53 qubit machine. Ragiti, another private startup company, they are also developing the machines. It might be a bit old, but like at the time of making this slide, they had 28 qubit machine. They might have larger number of qubits by now. Google, they have 54 qubit machine, and they also have 72 qubit machines. IonQ, they have about 79 or so qubits. D-Wave have large number of qubits, 2000 plus qubit, but they are slightly different. They are basically, they cannot solve all the like the problems. They are very specialized machines. So that's why they have very large number of qubits, but their applications are very limited because these machines are wired to do certain tasks. They are not universal machines. And all the other machines have very few qubits, but they're universal. Like you can reprogram them to do different tasks. But the D-Wave machines cannot be easily reprogrammed. They are basically programmed to do certain tasks, and they can only do those tasks. So they have large number of qubits, but they are limited functionality. As you can see, the progress in making larger and larger quantum machines is very rapid. I mean, they're pretty slow in the beginning, but now recently the curve is scaling exponentially, or at least like better than linearly. So hopefully in the next decade or so, we will see much larger quantum computers being reported from different companies and research institutes. Little bit more about silicon quantum computer, because that's what I work on. So silicon quantum computer is basically, you have a big piece of silicon and then you store qubits in, you make qubits in those silicon either by placing single atoms, which are phosphorus atoms, or you can have gates which can confine electrons at certain locations in silicon, and those electrons can be used as qubits. Number of qubits so far, 3 or 4, that's the level. I mean, we are scaling up, but right now is 3 or 4 qubits roughly. fidelity is really, really good. We can have very high accuracy qubits, 99.9% accuracy. So some of the good things about silicon qubits, as I said, they are very small, material is very good, scalability is nice, long coherence time. Some challenges are right now having more qubits packed in silicon is a challenge. So as people like research teams are working on it, but it's still it's a bit more work required. So one of the drawbacks of silicon qubit, or one of the highly challenging tasks in silicon qubit, is that in order to make 2 qubit gates, you need interaction, controllable interaction between the qubits. And the interaction varies a lot as a function of the placement of the qubits. You can see there's a huge variation in the interaction between the qubits. So that means if you don't have a good control on the placement of the qubits in silicon, you might end up large errors in your quantum gates, which is bad. So a few years ago, there was a big question, can we locate the qubits? Can we find out where the qubits are in the silicon? And it was a very big problem. So my research enabled that. So I basically able to propose that you can actually measure the qubits wave functions by using this state-of-the-art Nobel Prize winning tool, STM. And then you can basically use those images to trace back the qubits. And now we can find out exactly where the qubits are in silicon, and that enables us to make large-scale quantum computers without having errors or in the quantum gates. So can we make large-scale silicon quantum computers? Answer is yes. There was a proposal in Nature in 1998 by Bruce Kane, also Australian scientist from UNSW. He gave a proposal how you can scale up these qubits to make a large-scale quantum computer. Our team at University of Melbourne also came up of a proposal in 2015, and we have now developed another proposal recently to make large-scale quantum computers out of like the silicon qubits. One of the things which has come very recently, and that is basically doing the autonomous characterization, because the characterization of the qubits is a very difficult and challenging task. And now imagine like you have millions of qubits and you want to characterize them. You don't want to do it individual qubit basis. That's very, very difficult and onerous task. So what you want to have is like you want to use some automated technology which can look at all those millions of qubits and do the characterizations. And we basically developed a machine learning based technology using these convolutional neural networks, which can basically look at large number of qubits and autonomously characterize them. So we just published this in 2020. So Australia is working on silicon qubits. Huge amount of research is happening in Center for Quantum Computation and Communication Technology. I have been part of this center for the last 6 years. Main node is in UNSW. Sydney, where all the experimental research is happening. Partner nodes are University of Melbourne. I'm part of that, Professor Lloyd Hollenberg's team. We are doing a lot of theoretical work. There are other nodes at UQ, Griffith, ANU, RMIT, and UTS. So it's a lot of research happening in developing a silicon-based quantum computer. Recently, there is a silicon quantum computing company that has came out of this center with generous 80 million investment. And the target is that this company will be able to make 10 qubit devices by 2023, and then 100 qubit devices by 2030. So this is this kind of like scalability this we are targeting. Okay, so we have seen qubits, we have seen quantum gates, we have seen implementations of quantum computers. Now let's look at the big question, right? I mean, general community might have the question, why quantum computers are going to be so much powerful than classical computer? I mean, we have already seen a flavor, right? I mean, I told you that having just 300 qubits, you can have 2 power 300 large computational space. So that's kind of like inherently gives you your quantum computer power. But there is more to it. So let's have a look at it. So classically, we know that how computers solve problem is by algorithms, right? So you have a problem that you want to solve on a computer. You develop an algorithm that solves the problem, and then you execute that algorithm on a computer. And if the algorithm has been executed properly, at the end, you will get the answer. For example, binary search algorithm. So if you have sorted data, you want to find a particular entry in that sorted data. You have an algorithm called binary search, which basically finds a particular data element, insertion sort, right? So you have unsorted data, you want to sort it. You have an algorithm, insertion sort, that when will run on your data set, it will sort all the entries in a proper order. So these are all the algorithms which you can run on your classical computers to solve a real world problem. Now, this algorithm has an associated execution cost, right? So there are certain number of steps to solve that problem. And then there is also cost of executing that one particular step. For example, in binary search, you will have the basic elementary stuff would be comparing two numbers or data elements, right? I mean, you have two data elements, you want to compare them, and you want to find out whether you have a match or not. So that's your basic step. And computer will take certain amount of time to perform that comparison of element. And then there are number of steps. So you will need log base 2n steps, roughly, to solve the binary search. So that's the number of steps involved to solve the algorithm or execute the algorithm. So what will be the total cost of running binary search on your classical machine? So the total cost or runtime would be Tn, which will be CE times Fn. So Fn is the cost of the algorithm itself, which is basically log base 2n steps. And then CE is the time to execute one step, which is the comparison of the two data elements. So total time is CE times Fn, right? The algorithms are often classified in accordance with their asymptotic cost. So instead of doing this exact cost, we often say that, okay, how much is the asymptotic cost? Like, for example, what is the lower bound or upper bound of that algorithm? For example, you can say that binary search algorithm is basically order log base 2n. And the reason for that is because the CE part of the time is highly dependent on the hardware, right? Fn is basically inherently coming from your algorithm. You have designed a very best algorithm that can solve the problem. You exactly know how many steps are needed in that algorithm, and that gives you an Fn function, right? But the CE part of it, like the actual time to do the elementary step, that comes from the hardware. If you are running it on a Pentium 1 processor, it will take a different amount of time compared to if you're running the same step on Pentium 4 or a supercomputer. So that means that's why people then, when they classify algorithms, they say, well, CE is machine dependent. We don't care about it. Mainly how efficient is your algorithm. That's what we care about. So you basically give an order or omega type asymptotic costs. But the important point here is that the reason why quantum computers are powerful, because when you have designed an algorithm and you have a total cost CE times Fn, no matter how efficient you make your classical computer, you are only going to improve CE part of it, right? So you can, in binary search comparison of the two data elements. So you have a very powerful classical computer that will basically compare the two data elements very fast, but it won't change Fn part of it because that's the algorithmic part. That's not hardware dependent part. So that means that Fn is the cost of the algorithm for a given problem. Fn is already a best possible solution that you have developed. You can't change it on a classical machine. And therefore, no matter what you do, a classical computer will only CE and it cannot make it better. So just to give you an example, if, for example, on a computer, the cost of running binary search is 100 times n, is still order n, or it's a 10 power 6 times n, is still order n. So you have basically drastically reduced the comparison time from 10 power 6 to 10 power 2, but still you are stuck with that order n part of it. And if you are now imagine you have an intractable problem. Intractable problem means a problem which doesn't have an efficient solution, like the solution or the algorithm is n factorial or 2 power n type exponential function. And now you cannot solve it on classical machine because when n becomes very, very large, the cost becomes so much, your classical computer can't handle it. And no matter what you do, you can't make it more efficient because it's still n factorial or 2 power n. And that's why you might have heard in your algorithm class that there are problems which are NP complete or P complete, all those classifications, because those are inherently very, very challenging problem. And for very large values of n, you won't be able to solve those problems on your classical computer. On the other hand, quantum computers, since they have very different properties like superposition, entanglement, all those properties. So you can design very different quantum algorithms where you can actually come up with a better Fn function. So you're not just changing CE part of it, you're actually changing Fn. For example, instead of n factorial, you might come up with a new function, which is probably n power something, n power 1 or n power 3, something like that. And that will make the intractable problem probably solvable on quantum computer. So by exploiting special quantum properties, entanglement, superpositions, you can design better functions, FNs, and that's why quantum computers are so powerful, because they kind of provide you a way of solving highly computationally intensive problems. So in general, quantum computer run quantum algorithms, which are based on two properties. One property is superposition, as I already told you, that you can make qubits which are not 0 or 1, either like they can have like combinations of them, and also entanglement. I already talked about entanglement, that you can have outputs which are basically they are entangled, they are dependent on each other. And generally, when you develop a quantum solution to a problem, this is the structure you follow. So you prepare a state, which is the superposition state of all possible inputs. And then you apply quantum operations. And you basically, what you're doing is you're enhancing the probability of your output that you're looking for, and you're reducing the probability of all other outputs that you're not interested in. And finally, when you do measurement, since the outcome that you're looking for has the highest probability, so the whole state will collapse to the outcome that you're looking for. So that's kind of like a general idea of a quantum solution to a problem. So let's look at an example, Grover's algorithm. So Grover presented an algorithm to find a particular data entry in an unordered data set, right? So in a classical solution, best possible solution can do order n, because you have to look at, it's an unsorted, you can't just skip data elements, you have to go one by one, and in the worst case, you will end up with large number of comparisons, right? So Grover came up with a quantum solution, and he said you can actually solve this problem in order square root of n. So let's look at it. How did he do it? So let's suppose that we are given a 3-bit number. So there are 8 possible data elements, and you want to search 101, right? So that's your target value. So this is a quantum circuit. I'm not going to go into the detail how is this constructed, but just I want to give you the idea how is it working. So you, as I said, you always start with a state which is 0, 0, 0. So the circuit is on the top, and the outcome of the circuit at the point where this vertical bar is. So you see this is a vertical bar. So the quantum state at the vertical bar is basically presented in the underneath probability plot. So it will tell you like what is the probability. So right now the state is 0, 0, 0. So 0, 0, 0 state has probability of 1, and all other combinations have probability of 0. They are not present. Then you apply these gates, and now you put all the outcomes in the same probability. So they have all equal probability, right? So that means now at this point, if you measure, you don't get the answer, right? You are looking for 101, but you don't get it because all the outcomes have equal probability. But then what you do is you have a circuit, quantum circuit, which can select the outcome you are interested in. So this 101 is now red. You can see that. And you have selected that particular outcome. And then you apply next quantum gates, which are designed in a way to work that way. So you increase the probability of your desired outcome 101 and reduce the probability of all other outcomes. You repeat the same thing second time. You again select it 101, and you again increase it further. So you can see that by just application of this quantum search twice, you have increased the probability of the desired outcome 101 to 94.5% compared to the all others, which are very, very small, like 1 or 2%. So at this stage, if you measure it, there is 94.5% chance that you will get the correct output. And there's a little bit chance that you will get the wrong output. You can repeat it the same thing one more time, and you can even increase the probability of getting the correct output to close to 100%, like 99% or something, right? So you can see that instead of searching all the data elements, you have just applied 3 steps or 2 or 3 steps, which is order square root of 8, and you are able to find the outcome. So that's how the quantum algorithm, this gives you a general idea how quantum algorithms work, and how can you basically get this enormous power of quantum computation. Another class of circuits which are really, really hard to solve classically are random circuits. So in these circuits, you are not trying to solve a real world problem, but you basically put in gates and constructing random states which are then having random probability, arbitrary probability for each state. So you can see that this is a circuit on the left side, right side, the probability of each state, and you can see that they're very arbitrary. And the idea here is that you can, when you increase the number of qubits in these random quantum circuits, the probability space increases enormously. You can see that even with 10 qubits, the probability space is so large, and all of these values are random. And now if I want to ask you that at the end of this circuit, what would you get? What is your outcome? It's very, very difficult because it's a random state that you have prepared. So what you have to do is you have to actually solve or simulate this whole circuit step by step to find out the final outcome. There's no structure to it, right? So you can imagine that if you increase the number of qubits in these random quantum circuits, the state will become so complex that you can't even solve it. I mean, it's so difficult. And that's what Google used in recent paper to demonstrate quantum supremacy. So this is a Nature paper, this is a Nature paper that came out last year, and that showed that if you prepare such quantum circuits of 53 qubits or so, and the circuit depth is 20, like number of steps in the circuit along the horizontal direction are 20, then in order to solve those circuits, you will take 10,000 years on a classical machine. A classical supercomputer will take 10,000 years to process that information. But quantum computers can do that in just 200 seconds. That's the enormous power of quantum computers. Of course, it doesn't solve any real world problem, right? It's just a problem which demonstrates the power of quantum computer, that quantum computers are enormously powerful than classical computer, but doesn't solve any real world problem. So quantum supremacy is basically using quantum computer to solve a problem which classical computers cannot do. However, what we are after is a quantum advantage, a new term which has been used in the literature, and that is basically using a quantum computer to solve a real world problem. And that hasn't been done yet. So people have done quantum supremacy last year, Google showed it, but quantum advantage is still an area of active research. We don't know yet what kind of practical problem can we solve on a quantum computer. So let's look at some quantum computing research. So this is the last part of my talk. So I'm going to present like what are the few areas where people are working on to use quantum computer or actually develop quantum computers to solve some useful problems. So some of the areas are listed here. For example, quantum chemistry, machine learning, pharmaceuticals. People in pharmaceutical industry wants to develop targeted drug designs, and they want to use quantum computer for that. Cryptography, square communication between end-to-end systems, that has a lot of implications from quantum computing, optimization problems, finance. So our ultimate goal with quantum computing is that we have a quantum computer, we have a quantum algorithm which solves a real world problem. So we run that quantum algorithm on a quantum computer, and that solves the real world problem. But we are not there yet because of two reasons mainly. The first reason is quantum computers are small, like they are only 50 to 100 qubits, not enough. And secondly, the qubits are noisy. They decohere very fast. Remember in the beginning of the talk, I was talking about decoherence, which is a weakness of the qubits. So there's a lot of noise and errors and decoherence going on. So that's why we are not yet able to solve the real world problem. So right now, most of the research that's happening is that we are having a quantum algorithm, and we are having a small noisy quantum computer, and we run the algorithm on that noisy quantum computer, and we want to find out how good is that quantum computer and whether we can make it better or not. So that is the topic of most of the research that's happening at the moment. Running quantum algorithms on the given machines, whatever the available machines are, and trying to make those quantum computers better, trying to measure their efficiency, trying to make better quantum algorithms to use them in a better way. So that's the research that's happening in the community. So different research areas that are really active. Quantum hardware development, I already talked, many different groups are working, different kind of qubits and scalability. Quantum software development, people are developing quantum softwares, quantum compilers to run quantum programs on quantum machines. Quantum error correction, trying to protect quantum computers from noise and errors. That's a big area of research. Quantum machine learning is a big area of research. Quantum algorithm, developing new quantum algorithms to solve real world problems. For example, Shor, Grovers, HHL, many different quantum algorithms have been developed in the last few years. Post-quantum cryptography is also another area of research which is quite active. So a little bit more on quantum error correction. Error correction is very important. Even your classical machines require error correction because some transistors are faulty, some bits are flipped during the processing. So you always need an error correction. What if you have 1 at a certain transistor and it all of a sudden becomes 0 because of leakage or anything? So you need error correction. Same kind of error correction is needed for quantum computers as well. Even more so because the errors are more complex. So you need to develop efficient quantum error correction schemes. But the key differences are classical bits are only 0 or 1, but quantum bits are in superposition. So in classical domain, errors can only have bit flips, like 0 becomes 1 or 1 becomes 0. But in qubits, errors are very complex because there will be not only 0 becoming 1 and 1's becoming 0, but also the phase changing, the qubits rotating on the sphere that I was talking earlier. Then in classical domain, you can duplicate the bits, but in classical you can't, because once you try to duplicate it, you just decohere it. And again, in classical you can measure it, but in quantum you can't measure it. So there are a lot of challenges in quantum error correction, but there's a lot of research going on to develop efficient quantum error correction schemes. Machine learning also being used in quantum error correction domain. People are using variational circuits, for example. And how does it work is that you prepare a quantum circuit which has a optimizable parameter, for example, theta here. So you have a circuit where you have a parameter theta that you can tune. So you select a starting value of theta, then you run your circuit, you pass the outcome to a classical optimization technique, some machine learning technique, which can then optimize theta and feed it back to the quantum circuit. So you can basically learn noise by this technique. You can efficiently optimize parameters of that quantum circuit to mitigate the effect of the noise. Then there are also techniques like artificial neural network, for example, hybrid classical quantum techniques. For example, some part of the problem is run on quantum because we don't have large enough quantum circuits or efficient enough quantum circuits. So what we can do is we can have some computationally intensive part of the problem running on quantum circuit and some easy parts of the problem running on the classical, and then both quantum and classical circuits working together to solve the big problem. Lot of research happening in, for example, developing new quantum algorithms which can solve classical problems efficiently. For example, many of the optimization tasks, they are dependent on linear algebra operations, right? So they are dependent on fast Fourier transform, matrix diagonalization, matrix inversion. So these algorithms, classical algorithms, are very inefficient. So they, as you can see, that their scaling is order n log n, order n cube again. So there's very inefficient. And when the matrix size or the size of the problem becomes very large, they become very inefficient on the classical machine. But you can actually come up with the quantum solutions where you can have, now you don't have to process the whole n. Remember, you only need 2 log of n qubits, right? So in order to do, for example, n is equal to 8 size of the data, you only need 3 log 8 is equal to 3 number of qubits. So that way you can have problem size already reduced to d, and then you can have efficient solution in quantum domain like quantum fast Fourier transform, quantum matrix diagonalization, quantum matrix inversion, where you have order log d square type or d cube type solutions. So you can already see that you can do a lot of these tasks very efficiently in quantum machines. Optimization problems also, quantum computers are very efficient. For example, I talked about D-Wave, which has 2000 qubits. So you can actually program D-Wave machines to do certain optimization problem very, very efficiently on those quantum machines. Quantum computers are also very, very hot area of research for quantum chemistry problems. So when you want to solve a molecular system, and you have large number of atoms in this molecule, it becomes very, very difficult to find the ground state energy of that molecule. And classically, it's very, very difficult problem. It requires huge amount of computational space. But quantum computers can do it very easily because quantum computers are inherently based on quantum mechanical principles. So basically, you can map those quantum properties or quantum equations of those molecules on quantum computer and solve it very easily. So I'm not going to go in too much detail, but just to give you idea that there is a very efficient quantum algorithm to solve quantum chemistry problem, which is called VQE, or variational quantum eigensolver. It was proposed in 2013 and it has been used in many, many research papers. this algorithm can find eigenvalues of a matrix very efficiently. So the idea is that you are given a Hamiltonian, you want to find the ground state of the Hamiltonian, you prepare a state of a quantum circuit with again a parameter theta, which is tunable, and then you basically you basically design this part of the quantum circuit which calculates the expectation value of that state given for that particular Hamiltonian that you want to solve. And once you pass that information to a classical optimizer, you can then basically find efficient optimized values of theta to solve the problem. IBM used this kind of algorithm to solve small molecules on quantum computers. So there's a paper in Nature 2017. So they were able to solve like hydrogen molecule, lithium hydride, and BeH2 type molecules. So still at a very small scale, because again, the quantum computers are small at the moment, but the hope is that as the quantum machines become large and the research progress, hopefully in near future, we will be able to solve really, really big molecules very efficiently on quantum machines. Okay, so yeah, so I just want to mention that particularly for those people who are at University of Melbourne, we have now a partnership with IBM, which is IBM Q Hub. So IBM launched in 2016 IBM Quantum Experience. This is a website which provides cloud access to IBM quantum computers free of cost. Anybody can make an account there and use IBM quantum computers. Then IBM in 2017 launched a quantum network, Q network. And the idea was to partner with universities across the world to provide them premium access to IBM machines so that they can use it for education, for research. So that's what happened at University of Melbourne too. We have partnership with IBM, which was established somewhere in 2017-18. And we have now the only Australian quantum hub established at University of Melbourne. So if you're part of our team, if you're part of IBM Q Hub, then you can access premium IBM quantum computers to do research, to do experiments on them, and to learn more about the real world quantum computers. Okay, so if you are, I hope I've tried to give you some ideas, some basic fundamental knowledge of quantum computers, some of the areas which are really active in research. But if you are interested to learn more about quantum computing, fortunately, there's heaps of material. Quantum computing is one of the highly active area of research at the moment. Lots and lots of materials online available, so you can access those resources. As I said, IBM has a lot of materials available. There is quantum user interface. So that's the simulator that we have developed. You can free of cost access at this link, and you can use it to make your own quantum circuits, play with it, learn from it. There is a lot of literature that you can follow. For example, these are the some of the journals that regularly publish quantum computing papers. And we also have developed some quantum computing courses at UniMel. So we are offering 2 quantum computing courses, and there's another quantum computing course which we will offer in next year from the computer science department. So you can basically attend these courses and learn quantum computing area. Finally, if you want to work with us, if you're interested in quantum computing, please reach out to us. We are happy to provide you more information about this area. We are also happy to give you projects to work on. We have lots of projects. So reach out to us, contact us via email, and we'll be happy to interact. So thank you very much for listening, and I'm happy to take any questions.
Thank you so much, Dr. Osman. That was absolutely fascinating. A lot of information in there. Yeah, we've got a couple of questions from the audience. So I'm not sure if you have time, because I'm aware of that it's 12 now. And if you have time,
I can stay a few more minutes. No worries.
Yeah, okay. So 2 questions. The first is, with quantum supremacy, can a quantum computer solve an NP problem in polynomial time?
As I said, like, quantum supremacy is very specific term. I mean, quantum supremacy, as I showed by Google, they are demonstrated only on random quantum circuits. They are not for any practical problem. That problem was designed, or those random quantum circuits were designed just to show that quantum computer can do something which classical computers cannot do. So as Google showed in the paper, in order to solve that random quantum circuit, classical computer would need 10,000 years, and quantum computer can do it 200 seconds. but it is not, quantum supremacy is not generally to solve any NP problem. That has yet to be demonstrated. Quantum computer hasn't reached that level yet. Hopefully next 10 years, you will see larger quantum machine, more efficient quantum machines, which will be able to solve real world problems or the problems which have NP solution, type solution. But this is still not happened yet.
Okay, and we had another question about if you had any resources to learn more about quantum computing, but you've just covered that in the last slide. I've got one question. If you could briefly comment on the security aspects and the dangers of quantum computing.
So that's one of the area which I was highlighting. So that's the cryptography. So right now, if you look at the cryptography or any kind of communication that's happening, for example, your email going on the internet or whatever, like banking happening in the internet, they're all protected by cryptographic algorithms. So there is like RSA or different kind of algorithms that protect the information so that any eavesdropper or any hacker cannot access your private information. The problem is that those cryptography algorithms are dependent on, for example, prime numbers calculation. And the idea is that if you have a very large size number, you cannot efficiently calculate the prime number. I mean, if you have a, for example, 256 bit number, then it will take many years to calculate the prime number of that very large number. But with quantum computers' enormous power, you can potentially break that RSA algorithm. You can potentially very efficiently calculate the prime numbers of very large number, which is not possible in classical machines. So Shor's algorithm, for example, shows that you can do it. So now the main concern from the community is that if quantum computer exists or when they will exist, they will be able to break all the cryptography, which means anybody who has a quantum computer can read anybody else's private information or break the banking system, can basically take away all the money from the banks. So that's a real concern. It is, of course, a real concern. But the good thing about it, there's a huge amount of research that's happening in parallel in the area of securing communication in post-quantum area. Like when the quantum computer exists, how would you still be able to secure your communication? And there is like there is a national institute in America, NISC. They are doing a lot of research. They have done a lot of work in there. They have some ideas how to do that. There is another area of research called QKD, so quantum key distribution. So there is a lot of area research happening there. I mean, you might have heard that China has done a lot of research. They have like secure quantum satellites at the moment, which can do quantum communication from one point to another point without like that communication, even quantum computer cannot break because they are quantum secure communications. So there's a lot of research happening in parallel. So hopefully in next 10 years, when quantum computers will become available, hopefully there will be solutions that you can still have secure communication as well in parallel. So that's the hope. Hopefully things will not break down.
Hopefully lots more researchers will be interested in your area and help you achieve that sooner than later. All right, so I think this that's it for the questions, and I just want to briefly mention that we've got a little survey at the end, so if you could please just fill that up, that would really help us to give us feedback and improve in the future. And also, if you'd like to get involved in what we do as a student club at IEEE, there's another link that's in the chat. You can check this out. So I think that brings us to the end, and thank you again, Dr. Osman. That was absolutely fascinating. Thank you for your time, and thanks for sharing and enlightening us in this such an interesting area.
Yeah, thank you.
All right then.
Pleasure.
All right. Looking forward to the next one. All right.
See you.
Bye, everyone. Thank you.